does that just really mean? 8 faces, great. It's got 6, right? There's 6 vertices, but is there a C6? No. Is there a C5? No. So, is there a C4? Yes. Okay, so that's right. So C4, there's actually a few C4s, right? There's a C4 right here. Now I've labeled all of these blues. So there's a C4 along this axis here. Where's the other C4? How many are there? 3. Exactly. Right? Along every axis, essentially, right? C4 right here, so 90-degree rotations get all these blue balls, right? Into the same orientation. And then there would be another one, right, that goes right here. Okay? So everybody see that? Okay. So what else is in an octahedron? Flashing. Okay? There's obviously C2. So just like we said, it's easy to see if you have a C4 that there's most likely going to also be a C2. Right? That's parallel or coincident, right, with that higher order axis of rotation. So here's that first C4, and we can see very nicely that there's obviously also a C2 right there. And along any of the other, right, along any of the other axes, there's clearly also going to be a C2. Okay? There they are. Everybody see those pretty well? I darken them here. C2 here, C2 here, C2 here. That's coincident with all of those C4s. Okay? What else? Are those the only C2s? What? Let's stick to, okay, maybe a C3. Let's stick to C2s. Are these the only ones? So just like we had in that snowflake, right, these were C2s that are coincident with the primary axis of rotation. But just like the snowflake had ones that were perpendicular, right, that cut across the edges and cut across the vertices, in the octahedron are there other ones? Where? Yeah, that's right. You guys are going like this, and you know what you do. Sure, in between the axes, right? Each of these, right, in between bisecting any 2 ligands or objects, right, right, there's going to be a C2. So there's actually quite a few of these C2s, right? There's about 6 in total, depending on which unique 2 objects you're bisecting. Okay? What else? What's the point? The octahedron seems pretty simple, right? But it's actually a very high order or highly symmetric octahedron. There are lots of different symmetry elements that are in an octahedron, right? That seems like it's pretty complicated, but in reality, it's actually, we like high symmetry. Why would we like high symmetry? Even though there's a lot of bookkeeping that we have to do. That's right, because there's only really one unique part that's then going to be translated throughout the entire molecule. So when you see high symmetry environments, number one, all right, there's a lot of bookkeeping. It seems kind of daunting, but number one, they're really easy to identify. An octahedron is an octahedron. A tetrahedron is a tetrahedron. They're easy to see, and they also simplify things, even though they're quite complex, because you only have one small repeating unit. It's much better to have one small repeating unit than one much larger repeating unit. Okay, so there's some C2s. What else is there? Someone said it before. Where are the C3s? Right.
There's an axis going between 2 opposing faces of the octahedron.
That's right. So between 2 opposing faces of the octahedron, you all did the nomenclature activities, right? So we could have FAC and MER isomers in an octahedral metal complex. These 3 objects here, the blue balls, right, represent the face of an octahedron. So if we had an axis that then bisected or went right in the middle of this triangular face and then through the origin and out the other side, well, that's a C3 axis. Another way to look at that is if you look down that face, right, an octahedron will look like this. Okay? And there'll be a C3 axis right down there. Okay? Does everybody see that? And then clearly, how many unique faces are there? There's going to be 4. Okay? And so there'll be four different, C3 axes. They're pretty much the same, but they're unique depending on the actual orientation of the object. Okay, what else? So, octahedron so far, C4, C3s, C2s, and different types of C2s. What else? Any other axes of rotation? There's clearly other symmetry elements, right? Spit them out. There's an inversion. What else? Mirror plane. See how that segues? Okay. Yeah, that's it. So in terms of axes of rotation, the octahedron, right, it has those 3 main ones. Obviously the C2 is fairly complicated because there's a bunch of different ones, right? But those we've been able to bookkeep all of the axes of rotation. And the important part is sometimes we're able to cheat, right? Because we know when we have really high order axes of rotation, like 4 and 6, things like that, we're also going to have coincident C2s and C3s. Okay? So you know right away there should be a trigger. A C4, there's a C2 right here as well. A C6, what else is there? C2 and C3. Okay? Great. Okay, so planes of reflection, that's the next symmetry element. We'll try to go as fast as we can, right? Planes of reflection is just really a mirror plane, right? We talked about an object like this, right? Arnie Reingold's head, right? Where's the mirror plane? In all of our faces, right? Just bisects, right down the center point, right? So that the left side is the mirror image of the right side. Okay, that's it. We're going to designate a mirror plane as sigma. Okay? I don't know why. That's what we're going to do. Okay? So, how about this object? Are there any mirror planes? Should we do this one? We did it in terms of axis of rotation. Should we do mirror planes? We did? I don't remember. Okay, so where are they?
Bisecting from any of the corners or any points.
Exactly, right? So take any vertex, right, and you could have a mirror plane that then goes to the opposing edge, right? And so there's a mirror plane, and there's 4 other mirror planes. Is that are these the only mirror planes? Where else is a mirror plane? Good. Right, we got this, we got some of this, right? Obviously there's a mirror plane that then cuts through the plane of the object. That's within the plane of the object right there. Okay? So now these are actually 2 different types of mirror planes, right? One is gonna, I think we're gonna get into this later, but I'll just tell you now, this one here that's in the plane of the object, that's a horizontal mirror plane. That's typically going to be perpendicular to the primary axis of rotation, which for this particular object is what? The pentagon is C5, right? And then you can see, right, because this mirror plane, right, is perpendicular. If it's here, C5 is here, right, they're perpendicular. But you can see that these other mirror planes are going to be coincident with the primary axis of rotation. They're going to contain the primary axis of rotation. We're going to call that sigma v. Okay? But we'll get to those designations in a little while. All right? So let's try this. Here's a molecule. What is it? Who's seen this before? Hope ever. How many mirror planes? What kind and where? Well, not just where. Right? So now what I want to do, okay, is now we're going to get our language even more precise. So, in addition to water being on the board, what else is there? What molecule is this?